Hello everyone, welcome to the course on Basic Electronics with course code 23CT23B. This is Umayas, Assistant Professor, Department of ECE, SJBIT. So in this session, we're discussing about Module 1, that is Semiconductor Diode and its applications. So we'll be discussing about bridge, full wave rectifier power supply, capacitor filter circuits, RC pi filter. So coming to the full wave rectifier power supply. Like half wave rectifiers, full wave rectifiers require filter circuits in order to convert the output waveform to direct voltage. Figure shows a full wave rectifier circuit with a reservoir capacitor and a surge limiting resistor. These components operate exactly as explained for the half wave rectifier circuit with a few important exceptions. So we can see the circuit here, which is consisting of four diodes D1, D2, D3, D4, and there is one resistor RS, which denotes a surge limiting resistor. RL is the load resistor, and there is a capacitor shunt connection of capacitor C1 to the RL. It's a bridge rectifier circuit with a reservoir capacitor to smooth the output voltage and a surge limiting resistor to protect the diodes. So we have this figure, ripple voltage, waveform angles, and time periods for a full wave rectifier with capacitor smoothing. The capacitor smoothed full wave rectifier waveforms are as shown in this figure. The equation can be derived for the half wave rectifier circuit, still applies for determining the angle theta 1. So theta 1 is equal to sine inverse of E naught minimum by E naught max is the equation. Theta 2 is equal to 90 degree minus theta 1. Theta 2 is T2 is equal to theta 2 T by 360 degree. So this comparison shows that the capacitor discharge time T1 for the half wave rectifier circuit is approximately equal to the waveform time period T, while for the full wave rectifier by using correct value of T1, the reservoir capacitance for a full wave rectifier circuit can be calculated from C is equal to IL T1 by VR. Similarly, with the correct value of T1, the repetitive current IFRM can be determined from IFRM is equal to IL into T1 plus T2 by T2. The average forward current passed by the bridge rectifier circuit is equal to the load current, but each pair of diode supplies current for no more than a half cycle of the input wave. The other pair conducts during the other half cycle. So it is shown in this figure. The average forward current for each diode is half of the load current. IF average is equal to IL by 2. So another difference between the half wave and full wave rectifier power supply circuits concerns the reverse voltage applied to the diodes. So considering the figure, when the instantaneous input voltage is plus Vp as illustrated, Vp is applied across forward biased diode D1 in series with reverse biased diode D3. Therefore, the reverse voltage across D3 is VR is equal to Vp minus Vf, and VR is approximately equal to Vp. So examination of the circuit in this figure shows that VR is approximately equal to Vp, and this applies to each diode when it is reverse biased. As in case, so this is a circuit which shows the diode reverse voltage in a bridge rectifier circuit with a reservoir capacitor is equal to the peak of the input voltage. As in the case of the half wave circuit, capacitor and ripple calculations can be simplified by assuming the time T2 is very much smaller than T1. This gives the approximation that the capacitor discharging time is equal to half the input um, waveform time period. Capacitor filter circuit, that is RC pi filter. Here RC and LC power supply filters. The ripple voltage that appears across the reservoir capacitor in a rectifier power supply can be attenuated by the use of an additional resistor and capacitor, which together function as an AC voltage divider. So the figure shows the circuit, and here the capacitor C1 being the reservoir capacitor and R1 and C2 the additional components. The combination of C1, R1 and C2 is referred to as a pi filter because of the pi-shaped arrangement of the circuit components. Assuming a constant output load current, the reservoir capacitor continues to charge. So here the combination of C1 R1 and C2 is referred to as a pi filter because of the pi-shaped arrangement of the circuit components. Assuming a constant output load current, the reservoir capacitor continues to charge and discharge, producing a sawtooth or ripple waveform across C1 regardless of the presence of the additional components. Due to their higher frequencies, the harmonic components are more severely attenuated than the fundamental frequency component by the voltage division across R1 and C2. This combined with the smaller input amplitude of the harmonics So the harmonic components are more severely attenuated than the fundamental frequency component. So this combines with the smaller input amplitude of the harmonics means that the waveform developed across C2, the filter output, is easily essentially attenuated version of sinusoidal fundamental component. By Fourier analysis, the peak value of the fundamental component of the sawtooth waveform can be shown to be Vp is equal to Vp is equal to Vr by pi. So when Vr is the ripple voltage peak to peak amplitude, the AC voltage developed across C2 is the AC filter AC output. Where Vr is the filter AC input voltage applied across capacitor C1. XC2 is equal to R1 by root of Vi by V0 whole square minus 1. XC2 is approximately equal to R1 by Vi by V0. The additional attenuation of the ripple voltage obviously depends upon selection of R1 and C2 values, where there is a DC voltage drop across the resistor R1 that produced by the output current, and this must be considered when determining a suitable resistance for R1. So there are three DC voltage output terminals in this filter circuit, which output three sets of DC voltages. Yeah, U01, U02, and U03. Among them, U01 is only filtered through capacitor C1. U02 is filtered through C1, R1, and C2 circuits. So the filtering effect is better. The AC component is smaller. U03 is filtered through two filter circuits so that the filtering effect is the best. And so the communication component is the least. So coming to the pi type LC filter circuit identification method. So before that, if the resistor R1 in the LC, that is RC pi filter, is replaced with an inductor, that is L1, as in this figure, the DC voltage drop due to IL is almost completely eliminated because the inductor winding resistance is likely to be very much smaller than the resistor. The circuit is now an LC pi filter, and it can be analyzed similarly to the RC pi filter. Assuming that the inductor winding resistance Rw is very much smaller than the inductor impedance XL, the AC voltage developed across C2 in the circuit is V0 is equal to Vi XC2 by XL minus XC2. XL is equal to XC2. So it's a design process which normally commences by selecting C2 equal to C1, then a suitable inductance for L1 that can be calculated by some of the equations. So for the AC component, L1 is very sensitive to it, and that the AC voltage drop on L1 is large, and the AC component added to that load is small. So for DC power, since L1 does not exhibit inductive reactance, it is equivalent to a conduction circuit. At the same time, the filter inductor uses a relatively large wire diameter and a small DC resistance. Therefore, there is substantially no voltage drop to the DC voltage, so the DC output voltage is relatively high. It is the main advantage of using an inductive filter. Thank you.